Hello, my name is Mark,
I'm Nessie.
and today we will be talking about Newton's law of cooling.
So, why is this important to know about Newton's law of cooling? What benefits does it give us?
Well, if we understand Newton's law of cooling, we understand how temperature can decrease or increase with respect to time, and we'll know exactly how long we'll have to enjoy our perfect cup of tea.
So, you can see two equations on the screen right now. The first one is Newton's law of cooling, and the second is the general equation that we will derive using 4 different methods. The problem gives us a cup of tea that initially is 200 degrees Fahrenheit, and after 4 minutes, it's 180 degrees Fahrenheit. Later, we will analyze how much time it takes for the tea to drop to 140 degrees Fahrenheit and 120 degrees Fahrenheit. And then we will also analyze what happens when we change the ambient room temperature from 70 degrees Fahrenheit to 50 degrees Fahrenheit.
The variables we will use to represent this set of initial conditions is capital D for temperature, which is a function of temperature with respect to time, lowercase t, which is time, or in some cases, the function of time with respect to temperature. A is the constant of the air's temperature. C is another constant defined by initial conditions, and K is derived later.
So the first method that we will be using is the separable method. We start with Newton's law of cooling, and we separate the x and t terms, x to the left-hand side and t to the right. Then we integrate both sides, and using the u-side method, we achieve the general equation.
The next method we used was integrating factor method. We were able to bring all the variables to one side and use the definition of the integrating factor method multiplied through, and from there we could combine them using the inverse of the product rule. After taking the integral of both sides, and canceling with some simplifications, we ended up with the general equation as before.
The third method that we use is the characteristic equation method. We start with Newton's law of cooling, and then we bring all multiples of x to the left-hand side. We solve for the homogeneous solution, x sub h, turning x to r, and solving for k. Then we solve for the particular solution, x sub p, and finally solve for x, which is the sum of x sub h and x sub p, and that gives us the general equation.
The last method we use is the Laplace transformation method. Again, starting with Newton's law of cooling, we separated the constants and variables, each to their respective sides, then transformed those sides, and here this applies the initial condition. Solving for capital X by dividing through by s minus k, we get a bunch of fractions on the right-hand side, which we then solve using partial fraction decomposition. From here, we're able to return to the time domain, and after some simplification, we again get the general equation. But notice in this case, we have the ambient temperature, and instead of C, we have the initial temperature of the tea minus the ambient temperature of the air. Now, solving Newton's law of cooling for their constants, A is given as the ambient temperature, which is the problem statement, so we don't need to solve for that. Using the initial temperature at time equals 0, we can solve for C. And again, as we found with the Laplace transformation, it ends up being the initial temperature of the tea minus the ambient temperature of the air. Using more data that we have at time equals 4, we then solve for the value of K, which gives us an equation that we are able to graph.
So the first graph that you see is just the general equation that we derive with 70 as the ambient air temperature. You can see it converges to 70 asymptotically. The second graph that you now see represents what happens when we change from a 70-degree Fahrenheit environment to a 50-degree Fahrenheit. We use the unit step method to represent this. You can see the red line that it starts out is what's going on when we're in the 70-degree Fahrenheit environment. And after 4 minutes, it changes when we move into a 50-degree environment. And then the slope is steeper, and as it starts converging to 50 degrees Fahrenheit.
We're starting with this derived equation of temperature with respect to time. We then find the inverse of this through some algebra to find time with respect to temperature. This means we can take the temperature that we're looking for, plug it into the equation, and it will give us the time required to reach that temperature. Solving for both sets of initial conditions, we can find the time to 140 degrees Fahrenheit, the time to 120 degrees Fahrenheit, and the difference between the two is the total time that we have to enjoy our perfect cup of tea. For the constant air temperature, this ended up being 8 minutes, and for discontinuous air temperature, this ended up being 6. In conclusion, you're able to relate differential equations to a real-life situation.
We started with Newton's law of cooling, solved the general equation using every method, and found the time to enjoy tea.
We discovered that a drop in ambient temperature directly relates to a drop in the time we have to enjoy our tea. Speaking of which, I'm going to head out because my tea is getting cold.
Finally, we learned that tea is better than coffee. Thanks so much for watching.